Hi everyone. Welcome back. Today's lecture will be shorter because basically I wanted a self-contained treatment of Laplace's equation. That's pretty much all I wanted to do today so that we can start this last chunk of the course, which is the separation of variables algorithm, which lets us treat all of this stuff in the way that we want to. Lets us revisit all of these second order equations. Um, in a way that we can actually, actually solve some of these boundary value problems that we've been writing down and talking about for so long. Um, okay. So what did we do yesterday? At the end of lecture, I talked about Laplace's equation, which I've mentioned several times before. So the Laplacian view is equal to 0. And my definition is that a function u satisfies Laplace's equation on some domain is called harmonic. It's said to be a harmonic function on the domain in question. So our solutions here even have a special name, right? These are called harmonic functions. So as I said, spoiler alert, harmonic functions are extremely special and very, very nice and very, very important for a variety of reasons. Okay, but first, let's talk about these as solutions to particular PDEs. One is because we have a quantity that now, there's no time quantity here involved in what's going on. And so this is purely a spatial quantity, which means that the what is it that's playing the role of initial data here, right, is boundary data. So rather than talking about a boundary value problem, initial value problem type thing, here the only data is boundary data, right? So the associated like Dirichlet PDE, right? So the Dirichlet problem Dirichlet problem on a domain, say omega in Rn, where n is greater than or equal to 2. We'll talk about the one-dimensional Laplace equations. Pretty simple, pretty boring, right? So you can pretty quickly tell me all of the types of solutions to the 1D Laplace. So 2 and greater is what we're mostly interested in here. So if our spatial dimension is at least 2 here, the Dirichlet problem on some domain omega is so, and this is the Dirichlet problem. Of course, you could say, wait, well, didn't I have Dirichlet boundary conditions for my prior to PDEs? Yeah, you could call this the Dirichlet problem for Laplace's equation if you like. So the Dirichlet problem for Laplace's equation on some domain omega in Rn is following. So we want it to solve Laplace's equation on omega, and we want its value, or what it is on the boundary, to be prescribed. So here, the way of thinking about this is we're looking for a specific harmonic function, right? So it's harmonic on omega, and on the boundary of omega it has a particular form, right? It is g. It is some given function g. Okay. The associated Neumann problem would similarly be satisfies Laplace's equation on omega and its normal derivative, right? If n is its like outward directed normal, its normal derivative is given by some prescribed function g on the boundary, where this g integrated over the boundary is 0. Okay. So say omega was like a two-dimensional ball, right? Then this boundary integral would be that integral over the boundary circle, right? Of that two-dimensional ball. If this is three-dimensional, then this would be, so if omega was a three-dimensional ball, then the boundary integral would be a surface integral, right, over that sphere. Okay, that boundary surface for the 3D ball. So then what is the idea here? The idea is we want to seek, the textbook calls them like designer harmonic functions in some domain that have the prescribed boundary values, or whose normal derivative has the prescribed value. Right, so we want to seek like designer harmonic functions that have the prescribed boundary values. Prescribed boundary conditions. Now, this will be a little complicated, and we won't quite be able to finish our discussion right now. This is something that we'll return to after we've talked a little bit, or after we've taken this detour to do separation of variables. We'll come back to a discussion of this, but we're at least going to kind of get part of the recipe here for doing this. Okay. All right. So another associated problem. So another related problem is, instead of seeking a function whose Laplacian is 0 on some domain, what about seeking a function whose Laplacian is some prescribed function, right? Some prescribed function f. So this is the inhomogeneous Laplace's equation, if you like. So nothing wrong with calling it that. So instead of having 0 on the right-hand side, I have this f. But this equation comes up so frequently that there's another term for it, and this is the Poisson equation. So the Poisson equation is just the inhomogeneous Laplace's equation. So rather than seeking a solution to the PDE, Laplacian of u is equal to 0, this is Laplacian of u is equal to some given function f. Right. And of course, to make this either Dirichlet or Neumann boundary conditions, I could give some other prescribed, we could have a boundary value problem that looks like this. So it's the Poisson equation on on omega with, say, Dirichlet conditions on the boundary, right? Some other function g is given prescribing boundary conditions. Okay. All right. So before I move on to kind of talk about this a little bit more, quick derivation. What's a way of thinking about this? There's a number of ways to come to this equation, but one way is to think of a function whose Laplacian is 0 being a concentration or density of some quantity in equilibrium, right? So think of functions u such that Laplacian of u equals 0 as being some concentrations or densities of some quantity in equilibrium. Okay. So what is an example of some quantity like this? Well, even tied into some of our terminology surrounding this stuff is one particularly important quantity is electrostatic potential. Okay, and this is one of the canonical quantities that comes up whenever you're mentioning kind of a derivation of Laplace's equation. So I believe this is also mentioned if you take calculus at UMD and you use the Gulick textbook, then you'll see a discussion of this stuff in chapter 15. I think there's a little blurb in one of those sections. So anyway, so then how does this help us, right? Well, we can think about these as steady state solutions to the diffusion equation. So i.e., think of these as maybe steady state solutions to the heat equation. I'll recall heat equation looks like this, right? Okay, so there's the heat equation. Okay. So then, because these are steady state, they don't actually involve a t partial. So for these particular solutions we're seeking, that t partial is 0. Okay, identically, and so what we're left with is that the Laplacian of these quantities has to be 0, right? So alpha is some positive constant. So here, this Laplacian would have to be 0. But then, what about, if we go back to our derivation of the diffusion equation, then if we're in some domain in Rn, right, and we have some concentration or density of some quantity which is in equilibrium, then if I pick a subdomain, say V, of omega, what do I have? I have that this u sub t is 0, right, since we're seeking steady state solutions. But also, again, from the derivation of the heat equation here, this is the t partial of the quantity, which is the integral over v of u dx, which is the integral over the boundary of the flux vector field. So this is the flux density associated with that quantity u. Okay. But then if we assume that our flux density is minus alpha times the gradient of u as we did before, then what do I do here? Use divergence theorem. And when I use the divergence theorem, what do I get? I get that 0 is equal to this integral over the boundary of v of that minus a nobly u dot n, right, ds. Using the divergence theorem, the divergence of the gradient, of course, is the Laplacian. So this is the integral over v itself minus a times the Laplacian of u dx. Okay, and so I have, since a is some non-zero constant, I have that the integral of the Laplacian of u is 0, right, over any subdomain v of omega. So then what has to happen here is there's some theorems in the theorems in the appendix allow us to go from integral of quantity, right, equals 0 to quantity equals 0 on v. So this is these are called integral to pointwise theorems. The textbook calls them IPW theorems. So it goes from a statement about the integral in some form of some quantity being 0, allowing you to say that the associated quantity is 0 on the domain, allows us to say from here, because the integral over any subdomain of omega of this quantity is 0, this means that the Laplacian of u is 0 on omega. Okay, which ends our discussion. It ends our derivation. Quick note. This does not say that the flux, this F, right, needs to be 0 on omega. In fact, it could be non-zero at every point on omega, and that simply doesn't matter because the point here is that via the divergence theorem and getting this thing, getting this expression here, this works in a way that even if the flux is non-zero everywhere on omega, it's non-zero in a way that over the entire region this cancels out. Somehow the effects cancel out to produce no net flow out of any subdomain V, right? So there's this cancellation property, right? It's not saying that F is 0, because if F was 0 everywhere, then U itself would be constant, and that's not nearly as interesting. Okay, even if a constant satisfies Laplace's equation, that's not the sort of thing that we're going to be interested in, right? And it's always good, of course, to look at these things and say, well, if I specify that u is some constant on the boundary, then what is the u solving my Dirichlet problem? It's just that constant, right? Because a constant function trivially solves Laplace's equation, right? A linear function in the variables solves Laplace's equation as well for the same reason, right? So then the question is what does this say? Most importantly, if the flux were 0 everywhere on omega, then the only u satisfying this would be constant, right? Because if the flux was 0, then the quantity in question would just be a constant. Okay, but that's not what's going on here, right? So this it's that this is just very, very special, right? So the flux is not 0, it just works out in a way that there's this cancellation that happens. Okay. And so we have question, how many harmonic functions are there? So the answer, well, in 1D, so remember in 1D our Laplace's equation is this thing. So what's the only thing that solves that? So only solutions are constants and linear functions. But in 2D and higher, many harmonic functions. So this is good, and the reason this is good is going back to our statement of the Dirichlet and Neumann problems here. Our idea is that, being able to solve these problems, the kind of the ideal setting is I have these designer harmonic functions that I can use, right, to say, oh, well, so I need a harmonic function, but I need it to be this function on the boundary. Oh, well, I kind of have these like cookie cutter harmonic functions in some way that I can just say, yep, given prescribed boundary function, I know exactly what that harmonic function is. Boom, there it is. Similarly, if I want to seek one that has a particular normal derivative, right, then boom, here it is. So if I want this program to, proceed, then you'd think, maybe kind of speaking informally, that if I want to be able to construct these solutions to this, that this is only going to work if there's a lot of harmonic functions, right? If in some sense there's not that many harmonic functions, then maybe something like this I could expect to not work or to have significant problems. But because there's a lot of them, maybe the hope is that that I can actually do this. One thing, though. So one thing. Of course, even our derivation of this is kind of related to the diffusion equation, right? All right, let's take our Dirichlet problem here. Let's say that I have a solution to this thing, right? And let's say that I change the value of the boundary, right, at like a single point even. Is that actually going to change the solution, right? If I change the value of this u at a single point on the boundary, so instead of g, it's a function that agrees with g everywhere except at a single point it doesn't agree with g. The question is, does that change the solution u on the whole domain? And the answer is that yes, it does, right? It does. So slightly changing the values of u on the boundary changes u on omega. Okay. That is, here I'm just on the boundary and nearby points. But here u changes on all of omega, right? And so, i.e., the solution u at any point in omega in some way depends on all points on the boundary. So any point in omega, all points on the boundary. And so again, we get this kind of weird, you want to call it infinite propagation speed, or this weird situation where there's this like non-local property, right? Like this is an example of like non-locality, if you want to call it that. It was something that did not happen with the wave equation, right? But it did happen with the diffusion equation, where we saw that thought of in the way we'd been thinking about these things, our initial disturbance, right, propagated, right, instantly, right, to the whole real line. For instance, if we're thinking about the diffusion equation, like 1D diffusion equation on all of R, that, you know, somehow propagated instantly, right, to the whole real line. So this is a similar sort of thing where the solution at any point in the boundary, or sorry, the solution at any point in the domain itself, this could be a point that's not even close to the boundary, in some way depends on the value of the solution on the boundary, right? It depends on that boundary data in some way. So we should expect then, a solution formula for U to depend on integrals of, say, the G, right? Right? The value of U on the boundary itself. Okay. Okay. And so, to that end, maybe this is a good time to go into some basic properties of these harmonic functions. Now, we'll save the explicit solution formulas for later. Okay, this is covered in chapter 10. We will cover it after separation of variables. Okay. So then, before we do anything like that, let's talk about basic properties of harmonic functions. And probably the most important one, although they're all important, but a big one, okay, is the first, which is called the mean value property. Okay, so we'll see exactly what that means. Second, we have the maximum principle. So we have, just like we have the maximum principle for the heat equation, we have a sort of maximum principle for Laplace's equation. We have the Dirichlet principle. And then lastly, we have regularity. So remember, whenever we're talking about how many derivatives a function has, that's a question of regularity, right? So specifically, infinite smoothness. So if we think about this in a way where we're trying to get by with like the least amount of regularity possible, the benefit of this, of course, is trying to be as general as possible with our solutions, right? We're trying to seek solutions that are somehow like as general as possible. So for Laplace's equation, to state that, for that to be a sensible thing, because the Laplacian is a second order partial differential operator, then all we need for that thing to be nicely defined is a C2 function, right? A function that has continuous second order partials of all type, right, with respect to every variable in combination. So we could begin with that assumption. Begin with the assumption that the u that we seek is C2. But it turns out that even if that was our initial assumption, being harmonic tells you it's smooth, right? So you start out with the assumption that it's C2, but the fact that it's harmonic leads to infinite smoothness, so that gives you something extra, right? This is not typical, right? Like maybe a more typical second order PDE is not going to confer that infinite smoothness necessarily. So that's one thing here. That's kind of the easiest thing to state. Okay. So what is the mean value property? Let's just go in order here. What's the mean value property? So this states that the value of a harmonic function at a given point is equal to its average on any sphere centered at that point. Its average on any sphere centered at that point, this is known as its spherical mean. Okay. So what does this, let's actually write this out. So mean value property. Let's do this in 2D. This states that if U is C2, of course if it's harmonic it's smooth, so, but doesn't matter. Let's let U be in C2, U harmonic on a domain omega in R2, right? Let x naught be a point in omega, and R be a positive number, a positive radius, such that the ball centered at x naught of radius R is contained in omega. Then U of x naught, right, this is a point in R2, that is 1 over 2 pi R times the integral over the boundary of the ball centered at x naught of radius R of U of x d s sub x. Now I'm writing this to say that here our boundary surface is actually a boundary circle, because this is the two-dimensional case. The textbook doesn't state the two-dimensional case, it only states the three-dimensional case, and just makes a reference to the two-dimensional case. But you can state this in any number of dimensions, and we're about to see how this works. So in 3D, how does this work? So I'm not going to rewrite all of this. It's still C2 harmonic on some region now in R3. And now the ball in question is the three-dimensional ball. So here, this is the two-dimensional ball, right? I'm not going to come up, I'm not going to introduce like an N in the notation for the ball. It's just context specific, right? It is, the ball has the dimension it needs to for what we're talking about. So anyway, okay. So then what is this? Then the value of U at the point x naught is 1 over 4 pi r squared over this boundary surface now, because now this is the three-dimensional ball, so its boundary surface is actually a sphere, right? So this is the integral over the sphere, and so this is a surface integral. This is like a line integral. This is like a contour integral along a circle in the plane. Okay, and so there we go. Okay, there it is. And of course, we could do this in any dimension by doing what? All we have to do, so now, of course, the balls that show up, or the boundary of the balls that show up, are going to increase in dimension. That's fine. But then this constant out front, right, is going to change by, well, here, the boundary of the ball is a circle, and this is the circumference of the circle of radius r. Here, the boundary of the ball of radius 3, or sorry, the ball in dimension 3 is a sphere, and this is the surface area of the sphere. And so all we have to do is adjust that that constant to make this a true average, right? So we saw an example of this, of course, from Kirchhoff's formula, and the actual derivation of the mean value property is kind of similar to the derivation of Kirchhoff's formula, which we didn't do, right? I skipped over that because the actual specifics of the derivation are not super important to us. So I'm actually going to leave the proof. I'm not going to discuss this. We're just going to use it. So the proof is on page 325 to 326. So we're just interested in what this says. Now, a couple of things to notice here, right? So let's draw a picture. I'm going to draw a picture of the 2D case, obviously, because it's just easier. So here's my domain, omega, right? And we'll say that we have a U that is harmonic on this region, right? Okay. Well, then, if I pick this point, x naught, right, I'm saying that the value of U at this point is equal to its average over any circle centered in that point that fits inside omega, right? So I can pick any one of these, and the value of U at the point indicated is its average over these dashed circles I'm drawing in, right? So this automatically shows you how this non-locality, remember we had this non-locality property, right, for these harmonic functions. Non-locality, or for these questions, non-locality in the sense that my value of the solution here depended on the value of the solution at points away from here, right, of some distance away from that point, right? So this is kind of a weird sort of thing. Of course, this is a very special form of this. This is a very special way in which this dependence occurs. Okay, and it turns out that the converse of the mean value property is true. If U satisfies the mean value property, then it is harmonic. And so actually, this mean value property is just as important as being harmonic, in the sense that they're actually equivalent, right? Being harmonic gives you the mean value property. Having the mean value property forces you to be harmonic. So these go hand in hand. These are equivalent conditions. So that is another way of thinking about how special being a harmonic function is, right? Because this is certainly not something that you could expect a completely generic function to satisfy. Okay. What is the maximum principle? So we've already seen what we called the maximum principle for the heat equation. But what about for Laplace's equation? So it's the following theorem. So let U be a C2 harmonic function on a bounded domain omega, right, in, we'll say R3, although we could state this for any dimension 2 or bigger if we wanted to, which is continuous up to the boundary, i.e., a way of writing this is to say that U is continuous up to like the closure of omega, right? So this is being very technical here. This is allowing for omega to be slightly more general. We can do away with this. We can do away with this entirely if we restrict ourselves to if we're a little bit more restrictive on domains here in question. So if we view omega closure as omega union its boundary, right? Now, if omega is compacted, it contains its boundary, right? If it's closed, it contains its boundary. But whatever. Let's think about this kind of in the way that I have, a bounded open domain here, right? So here's what omega looks like, right? So omega is everything inside of this. And then the boundary, which is not contained in omega itself, is, well, it's this boundary curve. Of course, if this was in 3D, I would have a region, right, an open region that didn't contain its boundary surface, and then instead of this being a curve, it would be a boundary surface. So this is the boundary of omega, and then this omega bar, this closure, is everything inside together with the boundary, right? Okay. All right. So if U attains its maximum over omega bar, right, the closure, at a point in omega, so at an interior point, we'll say, then U must be identically constant, okay, inside omega bar. So it's actually constant everywhere in this case. Now, a couple of things. Note, this says if some non-constant U attains its maximum on omega, it must happen on the boundary. Well, let's say omega closure. Now, I should say that this if is kind of silly here, okay, because any U that's in C2 harmonic on omega attains its maximum and minimum, right, on omega bar, because U is continuous up to the boundary, as we said, and this omega bar is compact. And there is a general theorem from topology that says if you have a continuous function on compact set, then it attains its max and min values on that compact set. Okay. So the maximum and minimum of that function are attained somewhere on that set. Okay. So this if is, you don't need this. This is not some extra requirement. The point is that any such U will attain its maximum somewhere. So if it's non-constant, then where that maximum is attained has to be on the boundary. So another way of saying this is harmonic functions do not tolerate local extrema. Local minima, maxima. Right? They just don't. Right? Okay. So the maximum value of U must happen on the boundary. All right. That's another special thing, right? That's not typically how this works. How this works for a completely generic function that's not harmonic is you have some options, right? You might remember this from Calc 3 when you're doing the, when you're doing Calc 3, when you're doing Calc 3 examples where you are trying to find all the local extrema, and then maybe you're doing some kind of Lagrange multiplier thing where you're trying to maximize on some closed and bounded region, right, in the plane. When you're doing that, the options are your maxima or minima, your global max and global mins can happen where? They're allowed to happen at critical points in the interior of the region, or they can happen on the boundary, right? So you have some options. But here, this is saying, no, there's none of that stuff happens in the interior. It all has to happen on the boundary. Okay, which again is not, this is not something that just happens for a completely generic function. Okay, this can be used just like we used it for the heat equation, or well, just like you all will use it for the heat equation when I post your next homework, which will happen soon. You can use the maximum principle for the heat equation to show uniqueness for the corresponding IVP, BVPs. Here, we can also use the maximum principle to show uniqueness and stability for the say the Dirichlet problems are the easiest ones to do it for. So for the Dirichlet problems for Laplace's equation. Well, if you're keeping count, right, uniqueness, stability, that's 2 out of 3 for well-posedness. So the only other thing I need there is existence, which is exactly the thing that, I won't be able to do until later when we show how to generate solutions to this. Okay. So here's a quick note. This is that the maximum principle we get is something that's fairly robust for harmonic functions in the sense that it actually applies to functions that are not quite harmonic. The maximum principle also applies to subharmonic functions. What is a subharmonic function? Instead of Laplacian of u being equal to 0 in some domain, I have, we'll say, minus the Laplacian of u. I'll mention something about this minus sign a little bit later. So for various reasons, it is useful in many cases to actually consider this operator as minus the Laplacian instead of just Laplacian. So it's called subharmonic if minus the Laplacian of u is less than or equal to 0 on a whole domain omega. These are called subharmonic functions. So the maximum principle, or a version, I should say, of the maximum principle applies to subharmonic functions. This more general maximum principle leads to what are known as comparison principles. And those comparison principles are very, very important for a wide variety of reasons. If you're doing research in PDEs, these comparison principles might be a central focus of study for you. Okay. So the next property, I'm doing this out of order, but this is infinite smoothness. So if u is C2 and u is harmonic on omega, we can say, if we want to. Then actually u is C infinity on omega. Okay. So if u is C2 on omega, and if u is harmonic on omega means that its Laplacian is 0 on omega, then actually it's C infinity. So beginning with the assumption that our solution is only has two continuous derivatives, the fact that it's harmonic instantly kicks it up to having infinitely many derivatives, as many derivatives as you want. It's got infinitely many continuous derivatives, so this is very, very nice. Questions about how many, if any, of course, how many derivatives a function possesses is a question about its regularity. So I've used this word quite often already in this course, but don't know if I've ever actually written that out. But when I talk about a function being regular, or I question you on what is the regulation, what I mean is how smooth it is, right? Maybe you have a function that only has two continuous derivatives, right, but not a third, right? So for real valued functions, right, you're used to having two derivatives does not guarantee you have a third derivative, right? Okay, of course, if you're doing complex analysis, it's a little bit different, right? Having one is all you need to get infinitely many, but for us, we're not that lucky, right? In the realm of real valued things, in the realm of real analysis, we're just not that lucky. Okay, so one last thing that is an important property of harmonic functions is called the Dirichlet principle. I'm not going to go into too much depth on this. I'm just going to define some of the quantities and kind of talk about it generally. So, let's consider the class of functions defined by the following. So I'm going to use the same notation he uses in the textbook, which is like script A sub h is a set of all functions. The functions in question are some functions w that are C2 on omega and C1 on omega bar, and on the boundary of omega, they are equal to the specified function h. Now, this is just some technicality stuff here to make sure everything works out. We could do this we can define this. Notice I haven't talked about what dimension omega is in. If you like, you can always think about this in R2. You can think about this in R3, but we'll just say it's in some Rn. Okay. Now, for the specific, let's let n be equal to 3 for the thing that I'm about to define here. But you can define a similar thing for any dimension n2 or bigger. What is this saying? If we're in the two-dimensional case, this is saying that I have, if here is, so omega is the interior of this region. The boundary of omega is this. Right, it's the boundary curve. Sorry. And saying that our function is C2 on omega is saying that it's C2 on all of this interior region. And it's C1 up to the boundary, right? So C1 means has one continuous derivative up to the boundary. Of course, the boundary is included in this omega bar. So this is omega union the boundary is everything. It's omega and the boundary here. And then w is equal to h on this boundary. This is just saying that this function is nice enough. You don't have to get caught up too much in the exact requirements. We just need to do this because, as you might remember, when you're talking about derivatives and continuity and stuff, there's always issues at these edges, right? At the boundary, there's always this problem because the thing happening is like a one-sided thing, and you always have to worry about problems with derivatives when it comes to like a one-sided thing that you're looking at, right? So not having room on all sides of a point in question is always kind of tricky, right, when you're doing this sort of analysis. But whatever, okay. So let's do this. Define E of W to be the following thing. It takes a W that belongs to this set of functions, right? This is a set containing a ton of functions, right? Infinitely many functions here. It takes this W and does what to it? This is 1/2 times the integral over my region omega of the length of its gradient squared. We can call this the potential energy of W, which is in this set. Now notice, what kind of thing is this? Well, you might say E of W. If I've picked a W that belongs to this set of functions, then E of W, this is just going to be a real number, Right, that's not what I mean. So maybe we'll replace this W with just here. We haven't plugged in a function, right? What is this E object? So what does it take as inputs? As inputs, it takes functions, right? So the answer is it is a function of functions, i.e., it is a functional. If you've never, so of course you've seen functionals before. They just might not have been called functional specifically, right? You think of, take a, right? Uh, take any integrable function you like on some, like of a single variable on some 1D interval and integrate it, right? Like write its integral, right, from a to b, right? So that's what you define your I to do. So I takes a function f and assigns to it a real number, which is its integral from a to b, right? That's an example of a functional. Of course, you've seen that before, but maybe you didn't think of it as a function of functions, right? So it's a function of functions or a functional, okay? And it turns out that these sorts of things can be treated with an analysis that is similar to calculus, right? So we did calculus to find things like maxima and minima, or local maxima and minima for functions. Can I do the same thing for functionals? The answer is yes. So an example of this is a subject called the calculus of variations, so which is a very, very interesting subject. The calculus of variations states that in order to be what's called a critical point, right, the corresponding thing to a critical point for a functional, the function at which, that is a critical point for this functional has to satisfy something called the Euler-Lagrange equations, right? So this is a whole subject. It's beautiful. It's great. But this is very much related to what I'm about to say here. But I just wanted to say this in this way. So the question is, at which W do we have the lowest potential energy? At which function W do we have the smallest E of W, i.e., the lowest potential energy? Well, the answer to that is Dirichlet's principle. So it says that E of W is minimized among all such possible functions in that set by a W satisfying Laplacian of W is 0 on omega, and W is H on the boundary. Okay. So, thus, if, say, U satisfies Laplacian U is 0 on omega and U is H on the boundary, then this potential energy of U is less than or equal to the potential energy for W for all W in this A sub H. This is Dirichlet's principle, that harmonic functions with specified boundary value H, so for this Dirichlet problem, the sought after harmonic functions minimize the energy functional. So says that the sought after harmonic functions with or satisfying the Dirichlet problem minimize the associated energy functional. And you might say, is there some tie-in here with all of this stuff we've been doing, right? I think I've given you like 2 or 3 versions of computing these energy functional things, these things I've defined that are not quite the same but very, very similar. These expressions I define and had you computing their derivatives with respect to time, right? All of this stuff is related, yes. And so all of this stuff ties in. This is kind of the last nice harmonic or property of harmonic functions. So now the very last thing before moving on here is so one last thing that allows us to write out fundamental solutions to Laplace's equation. Notice that Laplace's equation is rotationally invariant. What do I mean by that? Well, if I wrote this out, right, we'll do this in R3, but of course it doesn't matter. If I wrote this out, if I take a point, a generic point in R3, and apply some rotation to it to get some other point in R3, what becomes of my Laplacian of u in this new coordinate system? Well, it turns out that it's not changed. It's exactly the same Laplacian as it was before, right? This is completely unchanged. And so the idea, look for solutions to Laplace's equation that only depend on the distance of x, your generic point, to the origin, i.e., only depend on the length of the vector x. So your u of x is actually going to be a function, we'll call it v, that only depends on the length of x, right? Which is some r for fixed radius r, right? Where r is defined to be the square root of the sum of the squares, right? x1 squared plus x2 squared and so on. All right. And this is what we're going to do tomorrow, right before we move on to finishing up all of this stuff. So I went a little longer than I intended, but that's okay. We're almost done with it now. So I will finish up this discussion of what are called fundamental solutions to Laplace's equation in tomorrow's lecture, and then we'll move on to separation of variables for these boundary value problems that we've mentioned this entire time. So anyway, that is the plan. So I will see you all tomorrow.